mass energy and nuclear binding energy. Mass energy. Einstein showed that mass is another form of energy and one can convert mass energy into other forms of energy, say kinetic energy, and vice versa. In the special theory of relativity, Einstein demonstrated that neither mass nor energy was conserved separately, only the total mass energy was conserved. The relationship between the mass and the energy is given by the most famous equation in science, E is equal to mc square, where m is the mass, c is the speed of light, and E is the energy equivalent of the mass. Calculate the energy equivalent of 1 gram of substance. Solution. Energy E is equal to 10 raised to power minus 3 kg into 3 into 10 to power 8 whole square m square s raised to power minus 2. E is equal to 10 raised to power minus 3 into 9 into 10 raised to power 16 is equal to 9 into 10 raised to power 13 joules. Thus, if 1 gram of matter is converted to energy, 9 into 10 raised to power 13 joules of energy will be released. Nuclear binding energy. The nucleus is made up of neutrons and protons. These particles are held together by the nuclear binding energy. Nuclear binding energy is the energy required to break up the nucleus into its separate nucleons, or this can be expressed as the energy released when the nucleus is formed from separate nucleons. The mass of a nucleus is less than the total mass of its individual protons and neutrons that make up that nucleus. The mass difference, delta M, between the two is equivalent to the binding energy of the nucleus. The relationship between binding energy and mass difference is given by Einstein's equation Eb is equal to delta mc square. For example, let us consider 8O16, a nucleus which has 8 neutrons and 8 protons. We have mass of 8 neutrons is equal to 8 into 1.00866 U. Mass of 8 protons is equal to 8 into 1.00727 U. Mass of 8 electrons is equal to 8 into 0.00055 U. Therefore, the expected mass of 8O16 nucleus is equal to 8 into 2.01593 U is equal to 16.12744 U. The atomic mass of 8O16 as found from mass spectroscopy experiments is equal to 15.99493 U. Subtracting the mass of 8 electrons, 8 into 0.00055 U, from this, we get the experimental mass of 8O16 nucleus to be 15.99053 U. Thus, we find that the experimental mass of the 8O16 nucleus is less than the total mass of its constituents by 0.13691 U. The difference in mass of a nucleus and its constituents, delta M, is called the mass defect and is given by delta M is equal to ZMP plus A minus Z Mn minus M nucleus. Delta M is equal to mass difference. Mp is equal to mass of a proton. Mn is equal to mass of a neutron. M nucleus is equal to mass of the formed nucleus. Z is equal to proton number or atomic number. A is equal to nucleon number or mass number. If you want to break the oxygen nucleus into 8 protons and 8 neutrons, energy Eb equal to binding energy has to be supplied. This energy required Eb is related to the mass defect by Eb is equal to delta mc square. Binding energy per nucleon. If we know the binding energy in a nucleus and the number of nucleons, we can work out the binding energy per nucleon, which is the average energy needed to remove each nucleon. Binding energy per nucleon, EBN, is the ratio of the binding energy EB of a nucleus to the number of the nucleons A in that nucleus. EBN is equal to EB upon A. The higher the binding energy per nucleon, the more stable is the nucleus. A plot of the binding energy per nucleon, EBN, versus the mass number A for a large number of nuclei is shown here. Main features of the plot. 1. The binding energy per nucleon, EBN, is practically independent of the atomic number for nuclei of middle mass number. 30 is less than A is less than 170. 2. The curve shows a maximum of EBN about 8.75 MeV for A is equal to 56. For A is equal to 238, it is 7.6 MeV. 3. EBN is low for both light nuclei, A less than 30, and heavy nuclei, A greater than 170. The force is attractive and sufficiently strong to produce a binding energy of a few MeV per nucleon. The constancy of the binding energy in the range 30 less than A less than 170 shows that the nuclear force is short-ranged. A very heavy nucleus, say A is equal to 240, has lower binding energy per nucleon compared to that of a nucleus with A is equal to 120. Thus, if a heavy nucleus A is equal to 240 breaks into 2A is equal to 120 nuclei, nucleons get more tightly bound. This implies energy would be released in the process of fission. If two very light nuclei, A less than equal to 10, join to form a heavier nucleus, the binding energy per nucleon of the fused heavier nuclei is more than the binding energy per nucleon of the lighter nuclei. This means that the nucleons get more tightly bound. Again, energy would be released in such a process of fusion.